Greetings! Welcome to Electronic Circuits 1. This is lecture number 11 and I am Razavi. Today we will look at another circuit using diodes which we call the full wave rectifier. Last time we looked at the half wave rectifier and looked at its properties. Today we will see that the full wave rectifier is somewhat better than a half wave rectifier and hence is a common choice in designing circuits. So let's refresh our memory about what we covered last time. Here's a quick summary. We saw that a half wave rectifier consists of a diode and maybe a resistor in the simplest case. And for this circuit we could try to draw the input-output characteristic by varying the input voltage from minus infinity to plus infinity. And we saw that the output is 0 until the diode turns on, and then it just tracks the input with a slope of 1. The difference is that there is a level shift from here to here by an amount equal to Vd on, which we call a diode drop. Now, then we said let's look at the time response of the circuit. So we applied the sinusoid at the input. And this time we used a capacitor. Why? Because with the resistor, what we have at the output with the sinusoid is not very useful. It keeps going up and down. It has a certain DC, but it also has fluctuations. So we thought if we place a capacitor at the output rather than a resistor, we can try to create a constant value, which would be good as a DC value. All right. So then we saw that if the capacitor starts with 0 voltage on it and the input voltage starts rising as a sinusoid as shown here, then first the diode is off, the output voltage is 0 up to a certain point. When the input reaches 1 diode drop above the output, the diode turns on and the output is now pinned to the input or tracks the input. So we saw that the output tracks the input up to this peak. But then, if the input starts falling past this point, the diode turns off. And the charge on the capacitor remains constant. So the output remains constant indefinitely at a value given by the peak value of the input, which we call V0, minus 1 diode drop. So that is the output voltage that we get. Now in practice, this circuit has to drive something. It's a charger for a laptop or a cell phone or some other device. So we model that device by a resistor, as you can see here. And this resistor tends to discharge this capacitor when the diode is off. So when we look at the output waveform, when the input is a sinusoid, we see that the output starts from 0 and then goes up to 1 diode drop below the peak, but then once the diode turns off, we have 1 capacitor being discharged through 1 resistor. So the output does not remain constant. It decays downward. It decays until next time around when the input comes up and turns on the diode again and charges the capacitor again. So we see that now the output has some variation in it, which we called the ripple. And in fact, using some approximations, assuming that this decay is very slow and this ripple is very small, we saw that the ripple amplitude, peak-to-peak amplitude from here to here, can be approximated by this simple equation. All right, so this is what we learned from studying the half-wave rectifier. Now we're going to go to the full wave rectifier. And I should tell you right off the bat why a full wave rectifier is better. There are 2 improvements when we go to the full wave rectifier. Number 1, the amount of ripple that we get is approximately half of what we have here. So that's one improvement. The other one is that the maximum reverse voltage that is needed in a full wave rectifier is about half of what is needed in a half-wave rectifier. So if in this design I decide that this diode must withstand a reverse voltage of, for example, 20 volts, then when you go to the full wave rectifier, we need to withstand only 10 volts. So that's also an improvement in terms of the choice of the diode. So those are the benefits of a full wave rectifier. But of course, there's no free lunch, as we say, so something has to be compromised. And what is compromised is a little more complexity. Now we will have more diodes than just one. All right, so let's go and look at the full wave rectifier. So we will repeat all of those analyses for a full wave rectifier as well. We will look at this basic structure and then see what it does when we have only a load resistor. Then we see what happens when it has only a load capacitor, and then what happens if it has a capacitor and a resistor, to model the discharge created by any device that we connect to the output of the full wave rectifier. All right, so let's begin with the full wave. I will call it simple full wave rectifier. So where does this term full come from? What is full? Okay, well, here's what we will see. In a half-wave rectifier with a resistive load, this is what we saw. So I will draw a box here. This is a half-wave rectifier. And I remember that when I constructed the input-output characteristic of this circuit, it looked like this. This is just what we just discussed. This is a half-wave rectifier with a resistive load. So I can even draw it here so that you remember what it looks like. And we saw that when we apply a sinusoid at the input of this half-wave rectifier, the output consists of a bunch of half sinusoids. So we have a sinusoid here, and what we see here is that we kept only the positive half cycles and we got rid of the negative half cycles. So that is the behavior of a half-wave rectifier. For a full-wave rectifier, the story is different. So here's a box which we will call the full wave rectifier, and we don't know the circuitry yet. So that is mysterious at this point. But what we expect to achieve is the following. If we give it a sinusoid like so, then what we would like to have at the output is as follows. Again, with just a resistive load, no capacitors yet. So what we hope to achieve at this output is like this. Positive cycles go to the output, like before, but negative cycles which were blocked before, which didn't come out in the half-wave rectifier, will now be flipped and are allowed to come out. So the negative cycles will be flipped and become positive cycles, and they come out. So negative half cycles become positive half cycles, and they come out. So that's why this is called a half-wave rectifier. This is called a full-wave rectifier. So what's inside this box, which we don't know yet, performs this type of operation, as opposed to what we had here. Okay, so this is the box, this is the circuit that we would like to synthesize, we would like to build. And the question is, how do we do that? All right, well, let's take our time and think about what we had here and how that gave rise to this type of output voltage. Well, the characteristic with a resistive load was such that we do not allow negative voltages to go through, And once a positive voltage comes in exceeding one diode drop, we let it go through. Here, we still want to have those, but when the voltage is negative, we want it to become positive and come out. So if I were to construct an input-output characteristic for this circuit, similar to what I have here, what should it look like? All right, so let's try to guess at this point. It's just a guess, but doesn't hurt. Let's try to guess what this input-output characteristic should look like. Okay, so we still have these coming out, so that part hasn't changed. That part is like before. But when the input voltage becomes negative, so this, remember, this is the input axis. When the input voltage becomes negative, what do we want? When the input voltage becomes negative, we want a positive output voltage. So if I'm here, I would like to have a positive output voltage. So if the input voltage is, for example, -5 volts, I would like to have an output which is maybe about +5 volts, maybe a little more, maybe a little less. So if the input is at -5 volts, I would like to have an output which is about plus some volts. So over here. So what we are thinking is that the input-output characteristic of this full wave rectifier should be something like this. Right? We see that if the input is sufficiently negative, we generate an output which is the same as the input except that it's flipped in sign. The slope is still -1. Maybe, right? We don't know yet, but maybe -1. And then this side is the same as before, so the slope is +1. So that's what we are thinking. Can we create a circuit that has this type of characteristic from the input to the output? If we can build that, maybe that's exactly what we need to implement a full wave rectifier. Okay, all right, so that is the objective. Let's go ahead and see what we can do in that regard. So I would like to make one observation which will help us greatly. So here's an observation. This is something really from basic circuit theory, but it's good to look at it in a new light in the context of what we are doing here. All right, so here's a voltage source which we will call Vin. And I have a resistor here, and I call the voltage on it Vout. Nothing surprising, nothing strange. Now, I will place one switch here and one switch here. I will call this switch S1 and this switch S2. So what happens if both of the switches are turned on? Well, it's very simple. If the switches are ideal, then this voltage is just equal to this voltage. We have a short circuit from the top of the resistor to the top of the voltage source, and from the bottom of the resistor to the bottom of the voltage source. So that's easy. So we say if S1 and S2 are on, then Vout is just equal to Vin. So far so good? All right, now let's make the problem more interesting. We will add two more switches, and for that I will change the color of my pen. So I will add a switch from here to here, and call it S3. And then I will add a switch from here to here. And I will call this S4. So what happens now if S1 and S2 are off, but S3 and S4 are turned on? What do we see? Well, now what we see is that the bottom terminal of the resistor is connected to the top terminal of Vin, and the top terminal of the resistor is connected to the bottom terminal of Vin. So Vout, positive here, negative here, is equal to minus Vin, because the resistor is flipped. So, or the voltage that we are measuring is flipped, right? So we say if S3 and S4 are on, and of course the other two are off, then we have Vout is equal to minus Vin. In other words, what we are really doing by these four switches is that we have a resistor, and we connect the resistor like this to the voltage source, or we flip it and connect it like this to the voltage source. Always monitoring the voltage from this terminal. So maybe I'll just put a red mark here so that we differentiate between this terminal and the bottom terminal. So I always call this voltage with respect to this Vout. So as the resistor between these two is connected to this way to the voltage source, Vin is equal to Vout. But if it's connected this way to the voltage source, then Vin is equal to minus Vout. So it's a very interesting technique. We're using four switches. We can send Vin to the output, or we can negate Vin, meaning multiply it by -1 and send it to the output. So is this what we were looking for in the context of a full wave rectifier? That's about right, because what we wanted to do was, if we have a positive cycle, we wanted to go to the output. If we have a negative cycle, we want to multiply it by -1 and send it to the output. And that's what the circuit is doing. So we have four switches in here, and if these two switches are on, Vout is equal to Vin over here. If these two switches are on, then Vout is equal to minus Vin over here. So the question is, what do we use to build these switches? And maybe diodes. Diodes can operate as switches. When a diode is on, it lets the current go through. So that's like a switch that is on. And when it's off, it stops. It is an open circuit. So that looks like a switch that is turned off. So maybe what I should do is just go ahead and replace these switches with 4 diodes. And maybe that will do what I'm looking for, right? So yes, in fact, that is the case. And that's what we call a simple full wave rectifier. So this brings us to the full wave rectifier, which is based on that principle. Let me change the color of my pen. So the full wave rectifier looks like this. Now, we can draw it like that, but it is more common to draw it as I will draw it right here. These are really the same thing, but that's how we draw it. So we have our input voltage source, Vin, and then we have 4 diodes. A good way of remembering how these diodes are connected, because there are 4 of them, is the following. We have 2 diodes going like so, and then both pointing downward. And then we have 2 diodes going like so, both pointing upward. The input voltage is connected to this point and this point, and the output is sensed, is taken between here and here. Strange, but true. Okay? So the output does not share any terminals with the input. That was not the case here or here, right? Here there was one terminal shared between the input and output, but for a full wave rectifier, that is not the case. We simply cannot share one of the terminals between the input and the output. Okay, so the output is here. That is the output. It's a little awkward to draw it because it's a little crowded, but that's okay. So let's just call these diodes something. D1, I don't know, D2, D3, D4. And this is what we call a full wave rectifier. Sometimes this structure is called a diode bridge. Okay, it has 4 legs. It's called a diode bridge. And what's important to remember is that the diodes in the parallel sides have the same direction. So this side and this side have the same direction, and this side and this side have the same direction. So that's what we need to remember. Okay, so as usual, we place a resistor between the output nodes. And now we would like to plot the input-output characteristic of this circuit, just the way we did it for the half-wave rectifier. All right, now you look at the circuit and say, oh my God, we have 4 diodes instead of just 1. So what is the first thing we do? We don't panic. We just sit down and think about it carefully and analyze it step by step. All right, so as usual, we will let the input go from -infinity to +infinity and look at the output. In this case, it's a little easier if we go the other way. We start from +infinity and go to -infinity. Things are a little more intuitive, so that's what we will do. Okay, so begin with Vin very positive. Well, we have 4 diodes. As usual, when Vin is very positive, so let's say +10 volts, we need to decide on the state of the diodes. Which ones are on, which ones are off? Well, we don't know, or can we guess? Well, let's look at the circuit carefully and see if we can guess. If we can guess, our life will be much easier. So here's what I'm thinking. We start from here. We say that this voltage is more positive than this voltage. So let's say this is 10 volts more positive than this. Okay, well, that means that this voltage is very positive. So my guess is that D1 will be on, will be turned on. And D4 will be turned off because this side is very positive. That's just a guess. All right, so if D1 is turned on, it carries a current. So here's the current flowing through D1. There's a current coming out of the voltage source, going through D1, arriving at this node. The question is, which way will this current go? Does it go this way? No, I'm thinking that D2 is probably off. Why? Well, because this side is very negative with respect to this side, so it's likely that this diode is off. So if that is the case, again, we're not sure, but if that is the case, then all the current from D1 has to go through the resistor. So far, so good. So we have a current starting from the voltage source, going through D1, going through the resistor, and coming to this point. Now what happens? Can this current go this way? No. If the current wants to go that way, it needs this voltage to be more positive than this voltage. But that's not possible because this is the most positive voltage we have in the circuit. So this diode is off. This current cannot go that way. Can it go this way? Yes, it can go that way. The current can flow this way through the diode. This diode has its cathode at the most negative voltage, so it can be on. So what we are thinking is that when Vn is very positive, D1 is on, and so is D2. And these other 2 diodes in the parallel branches are off. So what we are thinking is the circuit reduces to something like this. We have our voltage source, then we have D1, which is on, then we have the load resistor, call it R1, then we have this diode, which we call D3, and then we go back to the voltage source. So a current flows through these devices and comes back to the voltage source. That is our guess for the state of the diodes in this condition. I did not draw D2 and D4 because I'm thinking that they are off. At the end we have to check to make sure, but that's our guess at this point. Okay, where is V out? V out is this voltage between these two. Which side do we consider plus? Well, generally we consider this side plus and this side minus. That's called V out. So from now on, when you look at this bridge, you call this side plus, this side minus. And that has to be decided upon at the beginning and maintained the same throughout the calculations. You can't flip these signs in different parts of the problem. All right, so our objective is to plot V out as a function of V in. As V in starts from a positive value, very positive value, let's say plus 10 volts, and comes down. Okay, can I simplify that circuit? Well, I know that the diodes are on, and I will use the constant voltage model if you remember. So I will replace every diode that is on with a battery of voltage VD on. Okay, and then I won't draw it like this. This is somewhat silly. Why don't we just draw it like a straight branch? So we'll draw it like this. We're going through D1. D1 is a battery. VD on. Then we're going through the resistor, R1. V out is measured from here to here. And then we're going through D3, which is also a battery because it is turned on. So that's also VD on. And that is our voltage source at the input. Can I measure V out? How much is V out? Well, V out is not that hard to measure. We can write a KVL. So let's write a KVL very carefully, okay? We start from here, say minus V in, plus VD on, the battery positive on this side, plus VD on. Going down here, plus V out, plus V out. Going down here, plus VD on, plus VD on. We'll go back to the bottom terminal of the voltage source, so that's 0. That's our KVL. That tells us that V out, so let me use these extra lines here. V out is equal to, we see that we have V in minus 2 VD on. V in minus 2 VD on. So that's very simple. It says that when these two diodes are on, the output is tracking the input, but there's a difference of 2 diode drops between them. And that makes sense because this voltage source is followed by 2 other voltage sources. So the net result that comes available to R1 is 2 diode drops less than V in. So if you draw this behavior, that's what we get so far. This is V in, this is V out, and we started from very positive values, and we see that the slope is plus 1, so we have a straight line. And then we know that this line, V out goes to 0 when V in is equal to 2 VD on. So at 2 VD on, the line crosses 0. And this slope is plus 1. Okay, so that was not that hard. All right, so what we see is that as V out starts from as V in starts from a very positive value and comes down, V out also comes down. The difference between them is only 1 or 2 diode drops, and at some point V out reaches 0. Why does V out reach 0? Well, because if this voltage collapses, these batteries don't change, they still have their value, so this voltage collapses. And when this is just equal to this plus this, R1 has no voltage on it. So that's why. So when the input voltage reaches 2 diode drops, it's just barely enough to keep the 2 diodes on with a very small current, because we are over on this corner, and that means that the output voltage is 0. Now what happens if the voltage at the input becomes even smaller? So if V in comes over here, what happens? Well, we don't have enough voltage here to keep the 2 diodes on. We have 2 diodes in series, so we need 2 VD on to keep both of them on. So the diodes turn off. There's no current here, there's no current here. V out is 0. So V out stays at 0. So as long as V in is somewhere between 0 and plus infinity, we have this behavior which is actually reminiscent of the half-wave rectifier from here on, except that in the half-wave rectifier, this voltage was 1 VD on, 1 diode drop, whereas here it is 2 diode drops, because we have 2 diodes in series with the output, 1 here, 1 here. So that's the difference so far. Okay. All right, so now let's say that the voltage gradually becomes more negative at the input, and we'd like to see what happens. All right, well, what we can say safely is that if this voltage becomes negative with respect to this, then D1 will be off, because this voltage is negative, and probably D3 will also be off, because this voltage is turning positive with respect to this voltage, right? So we're thinking that D1 and D3 will remain off. They turned off around here, and they will remain off. So they never come into the picture again. But if this voltage is becoming negative with respect to this voltage, my guess is that D4 will turn on, because we have a negative voltage on this side. And similarly, D2 will turn on because we have a positive voltage on this side. So what we are thinking is that this diode and this diode will turn on, and that means that the current starts, because this side is positive, right? This current goes this way, goes this way, goes this way, and goes back. So let's change the color of our pen and see how that comes about. So we go back to blue. So if V in is sufficiently negative, the circuit reduces to, we have D4 on, so D4 is here, then we have the resistor, then we have D2, and then we have our input. R1 is here, and remember, the output voltage is measured like so, plus here, minus here, V out. Right, we marked this point as plus, so we have to keep that. We have to stick with that throughout. Okay, so the point is that because V in is negative, it means that this is positive with respect to this. And that's why this diode turns on, it pushes current this way, and the current flows this way, and the current goes that way. So can we find an equation for V out in terms of V in? Sure. Again, we replace these with with batteries of VD on, and then see what we get. So just like before, this is what we will have. We will have a battery for this guy. Because the anode is on this side, the positive side of the battery has to be on the lower end, and the negative side on the upper end. Then we have the resistor. So we have to be careful here. And then we have the diode. And then we have the input. So this voltage is VD on, positive here, negative here. This voltage is VD on. And the $1 million question is, where is V out? Which side of V out is over here? So that's why we have to be very careful. So remember R1? We said that this terminal of R1, which is connected to the cathode of D2, is called plus. And where is that? That is here. So this is plus, and this is minus for V out. That's where we have to be careful. Okay, so let's try to write V out in terms of V in. Again, if we want to be very careful, we just write a detailed KVL. Start from here, minus V in. So we have minus V in. Then we're going up here, sorry, minus. So I'll just do this minus VD on. Then V out has positive here, negative here. So again, going this way is minus V out. And then finally, minus VD on equals 0. So this says that V out is equal to minus V in minus 2 VD on. So these are the two important equations arising from our analysis here. And that's very interesting. So what does this equation say? It says that the output that we create across R1 with the same polarity as before, as we initially agreed upon, is equal to minus V in. So it actually multiplies the input by minus 1. It flips the input. And then there's still a level shift of 2 VD on. All right? So at what value is this V out 0? V out is 0 when V in is equal to minus 2 VD on. So when V in is equal to minus 2 VD on, so minus 2 VD on, the output is 0. And what happens before this value? Well, V out is just tracking V in with a slope of minus 1. So that looks like this, with a slope of minus 1. Of course, this equation or this equation are not valid from here to here because all of the diodes are off. All 4 diodes are off from here to here. The two diodes are on in this region, and 2 other diodes are on in this region. And in between, all 4 diodes are off. So interestingly, this is the characteristic that we had originally pondered. We thought maybe if we create a structure, a characteristic like this, we can build a full wave rectifier. And indeed, this diode bridge satisfies that. Now, do we also see similarity between this operation and what we visualized originally? Yes, so we said 2 switches connected to the resistor, like so, and then 2 other switches that flip the terminals. And that's what's happening. If you look at R1, you see that R1 is connected to V in positive here, negative here, right? For half of the cycle, approximately, for over here. And then it flips. It flips down, positive here, negative here, and connects to V in. So V out is equal to V in with some level shift, and then equal to minus V in with some level shift. And that's how we get these 2 characteristics. So that's a very nice way of creating a full wave rectifier. All right, very good. Let's think about the next circuit that we should look at. All right. Well, What I would like to do at this point is go ahead and connect a capacitor to the output of the full wave rectifier instead of a resistor. Again, following what we did for the half wave rectifier. So we're going to try to do something like this for this circuit. So for that, I will go to the next page and we'll see what we get. All right, so we will consider a full wave rectifier with capacitors, with a load capacitor. And we would like to see what happens when we apply a sinusoidal input to this circuit. All right, so here's our circuit. We have a diode here, oh sorry, that should be pointing the other way. All right, so we have a diode here, then we have a diode here, and finally another one here. And then we connect a sinusoid to the input, like so. That is our input. And then we connect a capacitor between the two outputs. Okay, so we can connect a capacitor like this, C1, and again the output always has this type of polarity, V out. And we'd like to see what happens. Well, given that we just studied what happens in the circuit for positive voltages and negative voltages, in particular, given that we saw, if I go back to the previous page for a second, we saw that for positive voltages, the output is pinned to the input with two diode drops between them. And then for negative voltages, it is pinned to minus input, again with two diode drops. We can see that this would hold even if we have a capacitor. What the circuit does, the way it delivers this voltage, is independent of this load, as long as these are ideal voltage sources. You notice from the KVL that we wrote that there was no role for R1 in this circuit. So even if it's a capacitor, it would be the same thing, provided that there is a voltage source here, there's a voltage source here, and there's a voltage source here. So keeping that in mind, we can go ahead and analyze the circuit with a capacitive load. Okay. All right, so again, we say, let's suppose that the input is a sinusoid. So as usual, I will use red for the input waveform. So here's a sinusoid, approximately, for the input. And I would like to see what happens at the output. Okay, again, assume the capacitor has 0 voltage on it when we start out, and we would like to see as Vin increases, what happens. Well, we know that as Vin becomes more positive, if Vin starts from 0, initially all of the diodes are off, again using the constant voltage model, so the output doesn't change. Let me change the color for the output to something else, maybe this brown. All right, so the output doesn't change. And once Vin reaches a sufficient voltage, how much is that voltage? What voltage do we need from here to here to turn on the diodes? We need to turn on this diode and this diode. So we need two diode drops at the input to turn on these two diodes. So once the input reaches, at some point, when it reaches 2 VD on, then this diode and this diode turn on. Okay, once they turn on, what role do they play? And they become voltage sources. So I can draw the circuit like this. Here's the input voltage source. This diode D1 turns into a battery, VD on, This diode D3 turns into a battery, VD on, and between them we have a capacitor, C1. Positive V out, negative V out. Okay, so we see that the voltage across the capacitor is still given by V in minus 2 VD on. This is what we saw before. So the voltage will start tracking the input all the way to the peak. So this is the output waveform. How much is the peak at the output? Well, again, remember that when we wrote the KVL, we saw that this output tracks the input minus 2 diode drops. So what we have here at this peak is V0 minus 2 VD on, V0 indicating this peak value here. So this is V0. Okay, good. Now what happens if the input starts falling? Well, the philosophy is the same as what we had for the half-wave rectifier. Once the input starts falling, both of the diodes have to turn off. There's no other way. And if both turn off, the voltage on the capacitor remains constant. So the output voltage remains constant. And that's like this, indefinitely. All right, very good. So that's the behavior of a full-wave rectifier. The only difference with respect to a half-wave rectifier is that this drop is 2 diode drops rather than 1. So we lose a little more voltage in this case than in the case of a half-wave rectifier. Okay, all right. Now, in the next step, of course, we should consider what happens if this circuit is driving a load like a cell phone or a laptop or something, meaning there's a resistor also modeling that load. So in addition to the capacitor, we also have a resistor. So we have to see how that works. Okay, so for that, I will do the following. Let me draw the circuit again. We have 4 diodes, and we remember that parallel branches have the same direction for the diodes, and this time we have a capacitor and a resistor in parallel. So R1, C1, the output voltage is still positive on this side, negative on this side, and then we are applying a sinusoid to the top and bottom terminals of the bridge. So that's a sinusoid. Okay, well, what we will do is try to plot V out. So let me write V out here. I hope it's not confusing. V out means between here and here. Let's try to plot V out for different cases and gradually see what happens when we have a resistor and a capacitor. So here's what I will do. Let's change the color to blue. We draw our time axis. Then we change the color to red. We draw our input waveform. So that's V in. And now we change the color and we try to draw the output. So let's first draw the output with only a resistive load. What does it look like? Remember? Well, the way it works is that the circuit turns on and we obtain something like this. Then it keeps on until the input is not enough to keep the diodes on. So then we have some 0. And then, if you remember from the characteristics, we flip this voltage. So we get something like this, a little exaggerated. Let me clear this area. So it goes here, and it goes here again. And that's our time axis. That's what we expected the full wave rectifier to do, right? We said it passes positive cycles and then it negates, it flips the negative cycles. Why do we have a dead zone here, so to speak? Well, because we know that the diode bridge does not turn on until the input is equal to 2 VD on. That's something that should be seen from the previous characteristics. So remember what happened here. We said if the input is less than 2 VD on or more positive than minus 2 VD on, in this region, the output is 0. So if the input sinusoid is not large enough, positive or negative, the output is 0. But once it goes past 2 VD on or minus 2 VD on, then the output tracks the input. So we use that to plot the sinusoid at the output. And that's what we get. So we see that when the input reaches a sufficiently positive value, so that would be plus 2 VD on, then 2 of the diodes turn on, and the output begins to track the input with a difference of 2 VD on. Similarly, when the input becomes negative enough, so around here, when it's minus 2 VD on, then the other 2 diodes turn on, they negate the input and create an output like so. So that is the output behavior when we have only a load resistor. So we'll say only R1. Okay, now let's plot this one as well. This is for only a capacitor. So I will change the color of my pen. I don't know if this green shows, hopefully it does. So if we have only a capacitor, then we start from here. We go to this peak. These are coincident, but I just have to plot them a little bit separately. And then it stays constant. So the green waveform corresponds to only C1. Okay, so now the question is, what happens if we have both R1 and C1? Well, we can see from the study of the half-wave rectifier that the output voltage goes up here when the 2 diodes turn on and charges the capacitor. But then once the input starts falling, the 2 diodes turn off. And for a while, nothing is connected to the capacitor. The capacitor is sitting by itself. So if the capacitor is sitting by itself, the diodes have turned off, the capacitor begins to discharge. So the capacitor voltage begins to discharge. So in the case of both R1 and C1, the output voltage looks like this. Again, I'm just drawing it separately. So we come up here, but then we begin to discharge. So this is what we call R1 and C1 together. Okay, so in the presence of a resistor and a capacitor, once we reach the peak voltage and we start coming down, for example, these 2 diodes turn off. And of course, these 2 diodes are off, so we just have a capacitor and a resistor. The capacitor discharges through the resistor, and we have a decay. So how far will this decay go? Well, it will go only to the next half cycle, as opposed to what we had in the half-wave rectifier. In the half-wave rectifier, we didn't stop here. We decayed all the way to this cycle, to this next cycle, right? Because nothing was happening for the negative half cycle. But in our case, in the full wave rectifier, we have turned on these diodes for this cycle. So these 2 diodes begin to charge the capacitor again. So the capacitor discharges, and once we reach here, the diodes have turned on, and they begin to charge the capacitor. Is this correct? I allowed the voltage on the capacitor to reach here, not further. For the half-wave rectifier, we said we needed a difference of 1 diode drop between the input and the output. What happened here? Do we need that? Well, this waveform already includes that. This is already the output waveform, right? So it already includes that 2 diode drops. So no, as soon as this voltage is equal to this voltage, the 2 diodes turn on again. These are the negative voltages, the other 2 diodes. So we track here, and then we again discharge, and we track here, and then we discharge. So that is the behavior when we have a load that draws some charge from the capacitor when the diodes have turned off. Okay. Can we calculate the ripple in this case? Well, if you go back to the analysis of the half-wave rectifier, we can see that it's actually not that hard to do that calculation. All we need to do is the following. Again, if this is a very slow decay, we can say that it comes and meets this waveform close to this peak, which means the length of the decay, the time length of the decay, is about how much? Is approximately equal to half the input period. The input period is from here to here. So from here to here is half the input period. If this decay is very small and slow, then it's approximately equal to half the input period. All right, so if you go back to the equation that we had for the ripple, this equation had V0 minus VD on it, and then it had R1 C1 F in. So what has changed here? So let me write the ripple amplitude. Ripple amplitude, this is peak-to-peak amplitude. So what we have is this. For the half-wave rectifier, we had V0, the peak voltage of the input, minus 1 diode drop divided by R1 C1 and then multiplied by T in, or divided by F in. For a full-wave rectifier, what happens? Well, the voltage that we have initially right here is no longer V0 minus 1 diode drop, is V0 minus 2 diode drops. So that has to be changed. So for a full-wave rectifier, this should be 2 V0 minus, V0 minus, okay, let me erase this. So it should be V0 minus 2 VD on. So V0 minus 2 VD on. All right. Okay. How about R1 C1? Well, that doesn't change. We have the same type of resistor and capacitor, so they stay the same. How about T in? Well, in the case of a half-wave rectifier, we had approximately T in seconds for this discharge. We started from here and discharged all the way to here, to the next cycle. Whereas now we have approximately, if it's very slow, we have approximately T in over 2 seconds. So this is multiplied by T in over 2. We have less time for discharge, so discharge will be smaller. Okay, so if we compare, we see that there's a factor of 2 in the denominator of the ripple for the full-wave rectifier. Now, typically, in most designs, V0 is much greater than this or much greater than that. So we say that this is approximately 1/2 of this. Not quite because of this factor of 2 here, but approximately half of that. So generally, we say a full-wave rectifier has about 1/2 the ripple of a half-wave rectifier, assuming that we have the same type of R1 modeling the load that draws a current, and the same C1, and of course the same input frequency. And that's one advantage of the full wave rectifier. All right. That was a quick tour of the full wave rectifier and its properties. As I mentioned before, this is used in many different circuits. And before we finish, I wanted to show you some pictures of diodes so that you see what diodes look like in real life. These are discrete diodes. These are diodes that you can buy, and they have many different applications. So let's see. No, I don't want to do that. I want to go to screen search. So let's see what diodes look like in real life. So here are some pictures of lots of diodes. Just to give you a scale, each of these diodes is approximately 4 or 5 millimeters, and you have a variety of shapes and so forth. Because a diode is not a symmetric device, on the package there should be some sort of notation to tell us which side is the anode, which side is the cathode. And as you can see here, you see there's a line here. This line usually shows the line in the symbol, so that would be the cathode. Similarly, there's a line here, that's the cathode. And depending on the application, you may have small diodes, you may have larger diodes. In fact, in power applications, you have something as big as this. Remember, for the diode to carry a lot of current, its junction area, that A, factor of A in IS, has to be very large. So you get the devices as big as this for high current applications. And finally, another type of diode is called the light emitting diode, LED. You've seen LEDs all over the place. They are diodes, except that they are not made of silicon. It turns out that silicon is not very good at producing light. So they use other technologies like gallium arsenide, etc., for these diodes, so that when we give them a current, they actually produce light. But there are still diodes. They follow what we have studied here. So that's a quick overview of what diodes look like in practice. I will see you next time.